Assalamualaikum warahmatullahi wabarakatuh and good morning. So now we have 23. So okay, so more than half. Okay, that's enough. So we should continue. So whoever cannot join, so you can always watch the recorded video later. Okay, so can you guys hear me? Just to check. Anyone, please?
Yes, loud and clear, Doctor.
All right, good. Okay, so today is our second week, and we are still on topic of a discrete time signal. Okay, just to overview. So this is actually our planning. So this is the plan. So we have a 14 week. So a discrete time signal supposed to be first week, because we have a holiday on the first week. So that's why we are still at this topic. So we will try to catch up. So hopefully we can finish this discrete time system within this week. Okay. So okay, and you'll see here that we will start the test one will be on 16 November, and we will start our assignment on week 7. Okay, if you check on in e-learning, so this assignment phase 1 is already there. It's available. Okay, you can check what should be what you need to do starting from now actually. But we will start at week 7, and we will go in detail later. Okay, let's continue to this discrete time signal. What we have done so far. So what we have covered last week is actually on this kind of sampling. One of it is a sampling. Okay, so what is a sampling? Sampling is whenever you have a continuous signal. So normally, because we don't store analog signal, what we store is a discrete or digital data, right? So to store digital data in your storage, so you need to do a sampling. And we have seen this example. So how we do a sampling. This is the frequency sampling is 1 hertz. What does it mean? So we need to take sample every second. Every 1 second, one sample. So this is what we get. Okay, this is from last class. And we have seen another example, which is if we do 2 hertz for the frequency sampling, means that we want to take sample every 2 sample every second. So this is what happens. So we will have more sample. Okay, so we have more samples. So that orange is actually double the sample compared to the green samples. So this is what we have covered last week, and also this part of this. So which is how does this discrete time signal looks like? So it is just a sequence of values. Okay, so why it is a sequence of value? Because after sampling, we are storing the value. So we are storing the value. So we store the value 1, we store the value 0, we store a value -1. So where do we store? We store it in our storage. And our storage is memory. And we already know that memory is either a ROM or RAM. But when you do storage, so it will be on your ROM. Okay, and we have addresses. Memory have address. So actually that index is actually representing the address. Okay, so that's why we have every time you see a discrete time signal, actually it is just a sequence of value. So where do you get this thing? From sampling. So how many samples that we have depends on your frequency sampling. Right, so for example, this one we have a xn 2.5, 3.1 until 1.4. So we have this is on index 0, 1, 2, 3, and 4. And if you want to translate that index into time in second, so we can do this, which is this is the first sample at 0 second. The second sample is actually TS. TS is the time sampling or sampling time. Okay, so if 2 hertz, the sampling time is supposed to be 1/2, which is 0.5. So if the frequency sampling is 2, means that TS is 0.5. So at the first sample, so actually we have a time at 0.5 seconds. So then we have 1 second here, and then this is 1.5 second, and this is actually 2 seconds. Okay, and so on if we have more samples. So, and this is what we call a signal values. Okay, so this is the value of the signal, and n is actually the index. N is the index, and this blue color text is the is our value in time, second. Okay, in second. And how do we convert that? So we have seen this last week also. So what is the relationship between the index, and the time in seconds? So this is the relationship. So which is t equals to n multiplied with ts. Okay, and then we have seen also a Nyquist theorem. So which is fs, our frequency sampling, supposed to be greater than or equals to 2fn, where fn is the signal maximum frequency. Okay, so that's we will have enough sample. So if you pick fs less than 2 of fn, so you won't have enough sample. Okay, the higher the fs, you have more samples, it should represent your samples better. Okay, represent the signals better because we have more samples. And this is what we're going to look at today about signal length. So what is the signal length? So we'll see what is this number of samples counted from the first to the last non-zero samples. And then we will see two types of operation on signal. One is the operation on the signal value, this one. So we will change the signal value. And another one is the operation on index. So we have this index. So we're not going to change the signal value, but we're going to rearrange the value based on the index. Okay, so you're going to change the index so that we are actually doing rearranging the signal value. Okay, so let's see. Let's go to our slide. This slide again. So this is, we have covered that. So we will start here. Okay, so what is the length of this signal? So what is the definition of a signal length? So it is number of samples. Okay, look at this properly. Number of samples. So signal length is actually number of samples. How many samples that we have counted from the first to the last non-zero samples. Okay, we are looking at the first and the last non-zero samples, and then we will count how many samples that we have. Okay, let's look at the at this example. So how many samples do we have here? This one. Anyone, please? One sample. Okay, one sample. So we only have one sample because this is the only non-zero value. So what is the value? The signal value. The signal value is on y-axis. The x-axis is the index. Okay, so hopefully everybody get used to that. X-axis, index. Y-axis, signal value. So because we have only one samples, one non-zero samples, then the length is 1. Okay, so this is the length is 1. Okay, how about this one? So the first non-zero value is actually at index -10. And then the last non-zero value is at index 1000. So how many samples do we have here? From -10 to 1000.
1010.
1010. Wrong. 1011. Yes. 1011. Because actually you have 0 here. Okay, 1000. This is 1000 plus the 10 plus one sample here at 0. So we have sample at 0. So it is a 1011. Okay. All right. So next, how many samples we have here? Sorry, this one, the third one. This is easy. Supposed to be easy. At index infinity, so we have a value of 100. Someone, please, either answer it using your microphone or, okay, 1, infinity. So to already answer infinity? The answer is 1, not infinity, because we are counting samples. Okay, what is a sample? Samples is when we have this non-zero value. Okay, so the non-zero value here is 100. Okay, 100. And then this 100 is actually on sample infinity. Before infinity, there's no samples. There's no samples at all. So actually the samples start at infinity. Of course, this is just a conceptual example. So we won't have this kind of, practically we won't have this kind of signal. Okay, this is just to test understanding only. So we won't have this kind of a sample, of course, right? So the answer is actually 1, not infinity. Doctor, could you explain again why 1011? Okay, so let's go back here. Why this is 1011? First, let's look at what is the definition. The definition is we need to count samples from a non-zero value, the first non-zero value, which is this is the first non-zero value. Okay, so what is this? So this is the first. Wait a minute. I need to solve this pen problem. I will be back in. I'll be back in 1 minute. Okay, so what's the problem? Is actually my hand is touching my screen. So okay, let's look back at this one. So let's say this is what is this? So this is the first non-zero sample, and then this is the last non-zero. Okay, sample. So let's say we have just let's say this is 1. This is 1, and then this is 10. Okay, to make the value smaller. So actually what we have is at -1. After -1 is after -1, it is 0. After 0, it will be 1, 2, 3, and then until 10. So this is where if you count 1, 2, 3, 4, 5, 6, 7 until this is it will be 9 before 10. So this is when you count this, because this is 1, and then we have a 10 here. So we have 10 samples here, 1 up to 10, we have 10, and you have 1 here, so it becomes 11. Sorry, this is 10, 11, 12. Okay. Sorry, actually this is 12. So is it wrong, the one that we answered? So this one's supposed to be 1000 plus, yes, the one is correct, 1011. If we have this, so actually we have 10 plus 1, which is 11, plus another 1, so 12. Okay, if it start from -1 up to 10. So, but if it start from -10 up to 1000, it will be 1011. Okay, so you need to count the, normally we miss this index at 0. Normally we miss this index at 0. Okay, hopefully that's clear. And if you look at this one, so this is another example. The value is infinity. The value is infinity, but still, it is actually one sample. So we have one sample with infinity value. So means that the length is still one. The length is one. The length is not looking. We're not looking at the value of the sample. So we are counting how many samples. We are counting how many samples. What is the value? So we're not looking at that value. Okay, that is length. How about this is this one is easy. Okay, try to answer this one. This one is easy. From -2 until, this is wrong. This is not -3. This is 3. So this one's supposed to be, if you just count, -2, -1. So this is 1, 2, 3, 4, 5, 6. Okay, because this is the first non-zero. This is the last non-zero. Okay, so this is where if you count, so you have 1 here, 2, 3, 4, 5, 6. Okay, so we have another one. So it starts because this is very important. Okay, let's look at this one. So we will conclude this one after this example. So now we have a sample. So all samples, this is actually the value is 1. So we have a sample from index 0. From index 0. Then we have another sample at index 1. Then we have another sample at index 2. And we have more samples until infinity, which is, but the value is the same. Everything is 1. Everything is 1. So how many samples do we have here? So we start from index 0 until index infinity. So clearly, this is actually infinity number of samples, right? Then the length is, so the length is infinity. So length is infinity because we have infinity number of samples. What is the value of the samples? All samples values are equals to 1. Okay, so it is equals to 1. So this is where later we will have 2 terms, which is we call it FIR and IIR. Okay, later we will have these 2 terms. Not today, not next week. I think another week. So we'll look at this thing. So what is F here? F is actually finite. And I here is infinite. So finite number of samples, infinite number of samples. So means that later we're going to deal with these 2 type of system, which is one is a finite impulse response, IR is an impulse response, and another one is an infinite impulse response. And how do we know that? By counting number of samples. By knowing what is the length of the samples, okay, length of the signals. So if the length is finite, if you look at this one, so number 1, number 2, number 3, number 4, number 5, everything is finite because it's not equals to infinity. The length is finite. Only this one, the length is infinite. Okay, so then this is actually IIR. The rest is actually FIR. So that's why this is a very important, so that we know what is the length of a signal. Okay, so any other questions before we move on? This is one of the basic of a signal, the length. Okay, let's move to the next slide. So this is a type of a discrete signal. So actually a type of 2 basic discrete signal, right? Basic. Impulse and step signal. And impulse and this impulse and step signal is actually not a new thing. So you have seen impulse many times before. You have seen a step signal many times before also. Okay, but now it is in discrete version. This is in discrete version. So you can go back to your previous courses, or you can go to maybe Wikipedia or any online sources, and then search for impulse. So there's a definition of impulse. And most of that is actually definition of impulse for analog signal, right? Analog signal. So what is impulse? Normally, previously, if you still remember, if you have this one, okay. This is actually at 0. So you have time at the x-axis. So this is your signal. The area is actually equals to 1. Okay, that is impulse, which is actually, this is very, 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 the wideness of this signal is actually very small, so that you can get area equals to 1. Okay, because this is a continuous signal. And for discrete signal, it is very, very straightforward and easy. Okay, what is the impulse signal? Impulse signal is just if you have a signal with one sample, and that sample is on index 0, and the value is 1. Okay, so we call it impulse. So this is impulse. And what is a step signal? Step signal is you have samples from index 0 until infinity, and every value of the sample is equals to 1. Okay, so we're just looking at some definition of a two basic signal, because we're going to use this a lot. We're going to use this a lot as a basic signal. And because this is a discrete signal, every index is actually integer. So if you look at the index, so after 0 is 1, after 1 it is 2, and then after 2 is supposed to be 3, and then 4, 5, 6 until infinity. So all this value is actually integer. Okay. So what is the value here? This one. So what is the value? Between 0 and 1. Anyone can answer that? So let's test your understanding.
0.
0? Any other answer? Is it really 0? So what others? It's not 0. It's not 0. 1? So it's not 1. 1 is here. So this is 1. This is a 0. This one, what is the index? 0.5? It's not even 0.5. Also wrong. Okay, so okay, let's imagine. Okay, so you have a 5 chair. Chair, the one that you sit now. Okay, you are sitting on a chair. So let's say we have a 5 chair. So you are putting those chair, the first chair. Okay, that one is the first chair, and okay, if we are putting it as an index 0, and then we put a second chair as index 1, and then the next chair, index 3, until index 4. So you get 5 chairs, right? So the index will be from 0 up to 4. So what is the index between chair of index 0, and what is the index between chair, the first chair, and the second chair, which is the index of 0 and 1? So what is the index? Okay, so someone answer that. No value, no chair, undefined. Okay, so actually there's nothing. So we don't do any indexing. Okay, no value at all. Not available. Not available. Nothing. Okay, undefined. Okay, that one can be accepted. Undefined. So after 0, there will be nothing. So after 0 must be 1. After 0 must be 1. Because we don't really taking any sample here. So that's why when you do the when you learn the microprocessor, first one is the memory address 0, and then memory address 1. Okay, so there's nothing between 0 and 1, right? So there's no value store. There's no address which is address 0.1. There's no such thing. So because all these are actually stored in a memory. So that's why between the 0 and 1, there's nothing. Okay. The value of y-axis is not 0. The index is not 0.5. Okay, let's see. There's some question here. But how about the signal value? Is it 1? Okay, so nothing. Okay, not 1, not 0, but nothing. Okay, it's like again, because everybody should already learn the microprocessor. Let's say this is address 0, this is address 1, this is address 2. So this is where you have value 1 and then value 1, value 1. So in between is nothing. Okay, so you can understand that. So physically, we don't have anything. So after address 1, after address 0, it is address 1. Okay, we do not store anything. You do not store anything. So this value is actually, we get all this value from the memory, right? So hopefully everybody understand that. So this is what we call a discrete time. So this is time, this is time, and it is discrete. So what does discrete mean? Discrete means integer value. Okay, unless it is an analog signal, so you will have all the values. You will have all the values. After 0, it is a 0.00000. You should have an infinity number of 0 first, and then 1. Okay, that one is an analog. And then after that one, 0.0000, you should have an infinity number of a 0 first, and then 2. Okay, and so on and so on. So how do you store analog value? How do you store analog value? There's too many values, because after 0 is not 0.1. After 0 is not 0.000001. Okay, even it's not a 0.000, you repeat until 10,000, and then 1, it's not, it's a 0 point. You should have an infinity number of 0 and then 1. So how do you store analog signal? Any idea? So this is actually your 4th year. So you've been actually dealing with analog signal for 3 years. So anyone has an idea how do you store analog signal? Anyone? Give some idea here. How do you store analog signal? Or maybe give some example of the signal and how it is stored. So digital is easy because we put it on the memory. Okay, sampling and converting it into digital. Yeah, then that one becomes digital. That one's become digital. So how about we have we doesn't have any digital system. Everything is analog. Let's say maybe 50 years back. Okay, 50 years back, there's no digital thing. Okay, yes, okay, that's one of the example. Vinyl records. Okay, something there's a tape. Okay, we use tape and then we put it there. So that one is the analog. There's no memory. Or if you have if you look at some movie, the earthquake movie, right? So there's some signal coming out from some needle. Okay, So that's how they store analog signal. They print it. They print. And then we analyze the printed signal. Okay, some expert will look at it, okay, and then put a measurement on it. Okay, this is the power of the earthquake is something. Right? That's the analog era. For now, if it is printed, it is just for maybe just we want to see something easy to look at it. So, but maybe no one is printing it anymore. Everything is just stored in a memory card, in a hard disk. Okay, because everything has been sampled. Okay. Wow, I didn't realize that. My grandfather used to use that needle machine to find all reservoir. Yes, that's maybe a long time ago. Everything now is digital. Okay, everything is on computer. We do the processing immediately. Okay, so that's the world today. So that's why everything is most of our system is now digital. But analog is still important. Analog is still important. We're not going to discuss that. What is the importance of analog system? Okay, because we are DSP, digital signal processing. Okay, we will focus on digital things only. Okay, next we will look at this one. If we look back to our summary, so we have two types of operation on discrete time signal. So one is we do some operation on the signal value. So what is the signal value? The value. This is 2.5. That's the value. That's the signal value. 3.1, 4, 2.7, 1.4. We will do some operation on this value. Okay, but the second one is the operation on index. So we will do something on the index. Okay, not to the values, but to the index. Okay, because a discrete signal, we have two values. Every time you have a discrete time signal, you should see two values. Because normally what we write is only the signal value, but we also have the index. Okay, so that's why we have two types of operation. Okay, let's do the first one on signal value. So we call it arithmetic operation, and this is quite easy. So what is the arithmetic operation? So we have addition, subtraction, multiplication, divisions, very straightforward and simple operation. Okay, it's just how to do it. So the operation are made on each of the sample of similar n. So that's what we need to do. Okay, so for example, we have the first signal, which is x1 here. We have 3 samples. So this is 3 samples starting from index 0 until index 2. Okay, 1, 2, and 1 again. 3 samples. And this is another signal. So we have 4 samples. We have 4 samples because the first non-zero is at index 0. The last non-index 0, the last non-index value is at index 0. So that's why we need to count this one. We need to count this. So we have 4 samples. The first one is 1, and then 2, and then 0, and then 1. So how should we do addition, subtraction, multiplication, and division between these two signals? Okay, we will do it on. We will look at on the same index and then do the operation. For example, this is x1n minus x2n. So x1n minus x2n. So we're going to look on every index. So index 0. So we have 1 here. Index 0 here. So we have also 1. So 1 minus 1 would be 0. Okay, so this is 1 minus 1. And then the next one is index 1. So which is we have 2. And then we have another 2. So 2 minus 2 will be 0. So this is 0. The next one, which is on index 2. So this is 1. And let's check on index 2 here. So which is 0. So 1 minus 0 will be 1. So this is 1. And then index 3, because it's not written here, it's not written. So then we need to assume that this is actually 0. Okay, because we need to do the operation here, because we have index 3 on x2. So 0 minus 1 will be minus 1, right? Minus 1. So very straightforward, very straightforward. So this is a plus. Plus is 1 plus 1 is equals to 2. 2 plus 2 equals to 4. And then 1 plus 0 equals to 1. 0 plus 1 equals to 1. Then you can do the division. You can do the multiplication. Okay, so the basic is just look on the same index. Okay, and then do the operation. Is that clear? So this is very straightforward. Any questions on that one? So let's move to the next one, which is, maybe this is new, because we have 2 operations on index. On index, we have 2 operations. One is a folding, we call it folding. And now another one is delay. Okay, so you might already heard about delay also many times before. Okay, but we're going to revise it here. So how do delay looks like in discrete version? All right, this is folding. Folding is actually, so let's see, if we look in this equation, the folding is actually defined as the outputs of the folding. So this is the results of folding. Is after we do multiply the index with minus 1. So we change the signs of the index. We change the sign of the index. Okay, so this is called folding. When we do folding or delay, because this is operation on index, so we will do something on the index, and not the signal value. The signal value is the whole thing is signal value. Okay, but within the bracket, so that one, the index. So when we do operation on index, so actually we do something to the index, which is within the square bracket, within the square bracket. Okay, so here as a reminder, we will use a square bracket for discrete signal. If it is a continuous signal, we're going to use the normal bracket. So let's say this is continuous, normal bracket. Okay, so this is what we call normal bracket. So this is a square bracket. If inside the bracket is t and t is in second, so this is actually analog or continuous. So we use the normal bracket. If inside the bracket is actually an integer, which is the n, so this is where we know that this is actually discrete signal, and we will use a square bracket. Okay, a square bracket. So okay, so what is the operation on the index here? So we multiply the index with minus 1 because we want to change the sign of the index. So okay, let's see what happened here. So this is one example. We have a signal xn, so which is we have a 1, 2, 3, 4, 5 samples. So we have 5 samples, and it starts at minus 1 index. The index starts at minus 1 and ends at index equals to 3. This is a signal value. The signal value is 2, 1, 1, 2, 1. We're not going to change this value, but instead we're going to rearrange. Because if you do something to the index, so these samples will be rearranged into a new position, into a new index. So what will be the index? Because this is, we are actually changing the signs. If we look at 0, if you change the signs, nothing happened. It's still 0. So that's why at y0, this is y0. The value is 1, so it is still here. It is still here. So it's not going anywhere, because changing the sign of 0 is still 0. But this one, the original index is minus 1. So these 2 is actually located at index -1. Now we're going to change the index for this value. So from -1, so we're going to move these two into index 1. So this is what we have. So this one is actually moved to a new index. This one, from -1, now it is positioned to a new index, which is 1. Which is, what is the new index? The new index is just changing the sign of the index. And if you look at this one, so this is originally 1, so change the index from 1, it becomes -1. So that's why at -1 here, so we have that value. And this one, index 2, so this value 2 now will be positioned to a new index, which is at -2, this one. And the last one is this one, so from from 3, and then we position it into to a new index, which is a -3. Okay, so it's like why it is called a folding. So if we do something like this, so originally it is at let's say this is the -1, so we have a 0 and then 1 and then 2 and then 3. So we have a 2 1 1. So this is 2, and then we have 1, 1, 2, and then 1. So what we do is actually we are flipping it. We are flipping it. Okay, so we are flipping it at this axis, at this y-axis. So that's why we call it folding. Okay, we fold it. We fold it at axis, at y-axis, So this is what we get. Okay, so that's one operation. So this is another one, which is delay. Delay is even actually, I think, easier to understand. So the new n is actually comes from n minus some constant. Okay, which is, we call it a delay. So we're going to move into several samples. So minus nd. Okay, so let's say we have a xn, which is 3 samples. We have 3 samples starting from index 0 up to index 2. And this is 1, 2, 1. The signal value is 1, 2, and 1. So this is what happened if we do a xn minus 2. So we are shifting it to the right. Okay, we are shifting it to the right. How many samples? 2 samples. 2 samples. So originally, the last sample is 2. Now the last sample is 4. Okay, see, you can see that. So it is shifted. It is shifted to the right. And if we do this xn plus 2, so it is shifted to the left. Right? It depends on how many samples that you that we have here. Okay. And of course, we need to do that. In this case, that ND must be integer also. Okay. So in this case, so we will see later that we can have ND other than integer. So we can have that. So, but in this example, so it's not possible that we can have. We will have an ND which is not integer. Okay, in this case. Okay, so any questions before we go to we do some quiz. Now it's 11:50, so maybe we can have 1 or 2 questions before we take a break.
Doctor, can I say something? Like ask
Yes.
you something? A previous slide, please. Yeah, previous one. Yeah. Yeah, you're saying that this is the delay operation, but when you're saying that n minus nd, and you say that this is a fast signal, so like there's a word difference I can see. Why is it different? Like the delay, and we're seeing fast signal, but the name is delay operation. Why?
Good question. Okay. So yes, actually that the name is actually first we are thinking this is an n minus nd. Okay, so one of these, of course, we can say that it is a delay, but actually another one, it doesn't seem like a delay. Okay, conceptually, it's actually the opposite of delay. So what is delay? Delay is actually you will have something which comes a little bit later. Right? So that's what we understand. What is the delay? Something which comes a bit later. Okay, let's look at this one. So this is 1, 2, and 1. And when we do xn minus 2, so this is, it looks like this is it comes faster. Right, as you mentioned. So why faster? Because if we look at here, at time 0, so this is 1. But now, at time 4, it's already have, at times 2, it's already have 1. Seems like faster. Okay, because we are looking at on the same axis. You need to listen this carefully, because this is a little bit complicated, because you can get confused on it. So why it is a delay? Why this is actually a delay is because at time 0, at time n equals to 0, we suppose to have value of 1. Okay, so this is the original signal. But why this is a delay? Because at time of 0, we didn't get any signal. We didn't get any signal. So we need to wait until time equals to 2. Then we get the time, the value 1. So this is actually the value is delayed by 2. Okay, and this one is supposed to get a value at 2, a value at n equals to 1, we get 2. But we need to wait until time equals to 3, and then we get 2. Okay, but of course, this is the opposite. This is the opposite. This is the opposite delay. We're supposed to get 1, this value, at time 0, but we already get it before time 0. As time equals to -2, so we already get that one. Okay, and we're supposed to get this one at index 1, but we already get it at -1.
Okay, Doctor, understood.
Okay, and another thing is when we do a discrete time signal, so make sure everybody get used that this n is actually time. Okay, whenever I say that this is a 0, 1, 2, this is actually time, because the one that's normally we get used that time is t in second. Okay, but now this is our time. And we can translate this. We can translate this into second if we know what is the frequency sampling. Okay, if we do not know what is the frequency sampling, then we leave it that way. If we know what is the frequency sampling, actually we will know at n equals to 1 what will be the time in second. Okay, so okay, let's do one question here before we take a break. Okay, so let's do just number 1. Okay, let's do it. Try to do it. Try to do it. And give your answer. I give you 1 minute. This is an easy example. So the rest you can do it later. So we have x1n, and then you need to fold it. You need to fold it, and then plus x2n. So this is our x2n. If you finish, maybe you just say, okay, finish. So maybe because to write n, actually you can write your answer, because every time you write answer, So let's say what is the yn? So you just type y equals to, what is the value? So there's a value a, b, c, d maybe. Okay. So because this is a discrete time signal, so you can write the value in sequence. Okay, you can write the value in sequence. We call this vector. Y equals to 1 to 3. Okay. Any other answer? So everybody agree? Y equals to 1 to 3. Okay, let's try to do that. Okay, yn, let's write that again. Yn is equals to x1 minus n, and then plus, oops, x2 n. So by doing the folding first, this is actually quite easy. So we have this one. If you fold this, so you just need to move this one to minus 1. Okay, so you'll have that one. And this is x1 minus n. We can write it as let's see, what is the value? 1, 1. 1 and 1, but this is, we can put a arrow there. Okay, means that this is index 0. So we have an index minus 1 here. Okay, and then x2 is x2. So what is the x2n? X2n is just from minus 2. And then we have a 1, 1, 2. 1, 1, 2. Okay, and then you just do the plus. Just do the plus. So this is an index 0. You need to do that with index 0. You get 3. And then this is index minus 1. This is also index minus 1. You get 2. And then this is index minus 2. Index minus 2, it doesn't have any value. The value is 0. So 1. Okay, and sometimes to make the notation easier, you can also put a underscore, underline to the value. So we know that this is index 0. Okay, so what is the yn? Yn is actually equals to 1, 2, and 3, but the index 0 is at 3. Okay, so this is the answer. Okay, any other question before we take a break? Before we take a break, there's a lot of other questions here. So we have until question 11. So hopefully you guys try it. Hopefully you guys try it later. Any question you can ask me. Any question you can ask me. Okay. You can the best is if you have any question, ask the question in the WhatsApp group, so that's everybody can learn it. Everybody can learn. Okay, we share to everybody. Okay, so now it's 12 o'clock. We will take a break for 5 minutes, and later make sure you go to the next link. Do not use this link. Do not use this link, because in e-learning, so there's a week 2 class 2 link. Week 2 class 2 link. Okay, the title is Discrete Time System Part 1. Okay, go to that link. Okay, we will use that link for the next class. Okay, so see you guys again at 12, 5 minutes. All right, so that's all for this session.